Welcome back, students. Today we are going to look into the quantum mechanical postulates. In the past couple of lectures, we've derived the Schrödinger wave equation and talked about how we can use the eigenfunction solutions to this equation to begin to think about solving some potential quantum mechanical problems. Before we look at our first quantum mechanical system, the particle in the box, we need to go over the quantum mechanical postulates that tell us what we can do with the various wave functions and eigenfunctions that we'll get from the solutions. There are 6 postulates. We'll discuss 5 of them here, with 3 today and 2 next time. The final postulate has to do with multi-electron systems, and we're not going to consider that for quite a while. We'll go over that in about 6 weeks when we get there. I don't want you to try to memorize these postulates word for word. That's not the point of the class, but I would like you to become very familiar with them, because these postulates are the main ways in which we can interact with the various wave equations that we will derive over the course of the semester. And of course, our ultimate goal is to extract chemically meaningful information from them. So like I said, in this first lecture here, we're going to cover the first 3 quantum mechanical postulates. The learning goals for this section are you should be able to state and apply the quantum mechanical postulates. Again, not memorization word for word way, but just know what they are and how we use them. We're going to focus on the first postulate, as that allows us to construct valid wave functions, and you'll see what we mean when we get there. And this third point is going to be a joint goal between today's lecture and next lecture. And we're going to be able to think about how we can explain the results of repeating experiments on a system, or doing an identically prepared experiment. And I think you guys probably remember something about this strange detail from previous classes. And we'll see how this goes. We'll start to talk about it today, and we'll see it in more detail in the next lecture. We'll start with the first postulate here. And our first postulate states that the state of a quantum mechanical particle is completely specified by a wave function psi of x and t. To simplify the notation here at the beginning, only one spatial coordinate is considered. So we only have a one-dimensional problem x. We could, of course, do x, y, z, and what will be more useful to us in the future to do polar coordinates or spherical coordinates are theta and phi. And we'll see that when we get there. The probability that the particle will be found at a time t naught in a spatial interval of a width dx centered at a point x naught is given by the following equation there, which is the square of the magnitude of the wave function. And we mentioned that a little bit before. So we'll take the complex conjugate of our wave function if it happens to be imaginary, and we'll multiply that by our wave function, and that's going to give us a probability. So how do we use this postulate? Remember, some of the keys from the wave function are that there is no physical meaning behind the wave function itself. So we have a wave, we're talking about a particle having a wave properties. Now, unlike something like a sound wave, the amplitude of that wave doesn't really mean anything physical. So the amplitude of a sound wave talks about its volume, the amplitude of a water wave would be its height, but our amplitude of our wave function doesn't mean anything. What means something is the square of the magnitude of our wave function. So again, our wave functions can be negative or imaginary to provide actual meaningful probabilities. In order for our wave function to have a meaningful probability, we have to ensure the following conditions. We have to ensure that the integral of the square of the magnitude of our function, so remember this term here is the square of the magnitude of our wave function. We have to ensure that the integral of that over all space, so the area under the curve of our wave function, equals 1. And what this math equation here means is that we have a 100% probability of finding our particle in space. Now, if we didn't, that wouldn't make sense. We wouldn't compare it to a probability. Now, the bounds here of integration are going to depend heavily on the system at hand. So we will constantly change these depending on what we're doing. So for example, the first scenario we're going to investigate is a particle in a box, where we're confining a particle into a box. So we don't have to look over all of space to find the particle. We just have to look in the box itself. So as we change the problem, we'll slightly change the bounds of integration. But the point here is that we have to have a 100% probability of the particle existing in space. And that makes sense. That's what it means to have a probability. Now, this also means that if we were to take a subset of space and look for the particle, we need to have a less than 1 probability. So if the particle exists in all space, if we were to just look in a particular corner of space, we shouldn't have a 100% chance to find the particle because it can be other places. So we need to have a less than 1 probability. Remember, since we're looking at the square of the magnitude, our wave function can be negative or even a complex function. Now, since we are comparing our wave function to meaningful probability, we actually get some other useful restrictions on the wave function. And these will be important as we set up wave functions in the future. So again, the idea behind this, that underlies this, is that our wave function needs to mean something in terms of probability. Specifically, the square of the magnitude has to reflect the probability of finding that particle in some specific region. So first, the wave function must be single valued. Now, to have a single valued wave function means that at every point of x, you only have one value. Now, these are the typical functions that we're used to working with from math. So for example, this function here is single valued at every single x point. There is only one y. Functions like a circle do not fulfill this, this demand. So for example, at this point x equals 2, there is a y equals -2 and a y equals 4. Now, why is this a problem? If you were to ask what's the probability of finding x near 2, and if this was our wave function, we'd say, well, it's 4, or you could say, well, it's -2. Now, of course, we have to square and normalize those to get a meaningful probability, but you can see if there's 2 values there, we have an inherent problem. We can't relate to a single probability. So all wave functions, in order to be valid and make physical sense, must be single valued functions. Another thing that we have to ensure is that the second derivative is well behaved. That's because our wave functions are going to be plugged into the Schrödinger equation in order to evaluate them. And we have to take a second derivative in the Schrödinger equation. So if we can't take a second derivative of our wave functions, then they're not valid wave functions. They don't work. So an example of that is a tangent of x. Tangent of x is single value, but it's undefined here at every intervals of pi. And so it does not fit. It's not a well-behaved function itself, and its second derivative is not well-behaved. So not only does the function have to be well-behaved, but also its first and second derivative need to exist and be well-behaved. The third restriction, that going back to a meaningful probability, is that we have to have a finite value over the interval that we're interested in. And this is important because, again, we're trying to relate to probability. So if I'm trying to integrate and get a value equal to 1, I have to have a finite area under my curve. If I have an infinite area under the curve, I can't integrate and get a value of 1. Now, that doesn't necessarily mean that functions that have infinite areas under the curve can't be wave functions. It just means that they have to be restricted to a certain interval. So imagine the function e to the x, that goes off exponentially, and of course has an infinite amplitude. So that is not a valid wave function from -infinity to +infinity. But if we were to limit the bounds there on that function, like say 0 to -infinity, now all of a sudden that has a finite amplitude. And we could even do like -infinity to 100 trillion, right? We still have a finite amplitude. So as long as we have a finite amplitude under our curve, we can normalize it and we can have a valid wave function. But infinite functions don't have meaningful probabilities. The next thing that we're going to want to know, and that what the second postulate will address, is what else do I do with the wave function? So here we have, with the first postulate, we have a tool for constructing valid wave functions and also figuring out the probability that the wave function will be within a certain region of physical space. But I don't really care about that too often. More often, I want to do something like know the energy of a particle or know the momentum of the particle. So how can I go about determining those? And that's what our second postulate will tell us. So the second postulate says that for every measurable property of a system, such as position, momentum, and energy, there exists a corresponding operator in quantum mechanics. An experiment in the laboratory to measure a value for such an observable is simulated in quantum mechanical theory by operating on the wave function of the system with the corresponding operator. So anything we could want to know about a particle is listed over here under the observables. So we might want to know the momentum, the kinetic energy, position, potential energy, total energy, and if we're really crazy, we might even want to know the angular momentums. Now, to figure these out, we can measure them experimentally, or in our math, what we can do is operate on them with these various operators. So our total energy operator we've seen here, this is our operator from our Schrödinger equation, our Hamiltonian. But we could also operate on them with position operator, a kinetic energy operator, momentum, and so forth. And we denote our operators here with a caret. So at this point, you may be thinking, what does it mean for the position operator here to simply be x? And how can we use that to determine the position of a quantum mechanical particle? And you might even be remembering back to Gen Chem and saying things like, I'm pretty sure that you can't know the position of a quantum mechanical particle. And these are all great things to be thinking. And we're going to use the remaining postulates to kind of parse through those questions. So hold on to them. And we'll touch on them a little bit today, but we'll really pick up next time and hammer them out. The third postulate here for us states that in any single measurement of the observable that corresponds to an operator A, the only values that will ever be measured are the eigenvalues of that operator. And so this will go into what we talked about last time, that our eigenfunctions form a complete set. So remember that our wave functions don't have to be eigenfunctions. If we go back a couple slides, we'll see that our wave functions only have to satisfy these equations or these terms here. And there are a lot more equations that satisfy these terms than are actually eigenfunctions of our particular system. And so in that case, what are we going to measure? Well, our postulate 3 tells us that it doesn't matter what our wave function is. If we try to do something like measure the total energy, we will only ever measure one of the values that corresponds to an eigenfunction of that operator, which is an eigenvalue. So for example, if we had our wave function that looks something like this, this is not an eigenfunction. It's a sum of 3 eigenfunctions. So if we tried to measure the energy, what we would get are the energies associated with phi1, phi2, and phi3. Those are the only energies we could ever measure, and every time we did an experiment, we would measure one of those. And so this, again, gets us into this weird quantization thing. And so for the particle in the box model, and we'll talk about this in great detail in the coming lectures, the energy would correspond to this equation here. So we can only measure either h squared over 8ma squared, or 4 or 9 h squared over 8ma squared. And you might be asking here, how do we know which one we're going to get? Now, the only thing that's different about these functions is these constants out here, and it turns out that these are determinative of how likely we are to measure either energy 1, energy 2, or energy 3. But with this, we're going to hold off on actually trying to figure out, how likely it is to measure each one of these, and we'll save that for next time. Before we go, I am going to address one more question here. And this question is going to be, what if I tried to measure momentum? And this goes back to the question we asked on the last slide of how can we even know the position of a particle? I'm pretty sure that's impossible. Something with Heisenberg's uncertainty principle. I vaguely remember this from Gen Chem. So what if I tried to measure the particle's momentum? Now, if this function here is written here in terms of the eigenfunction solutions to the total energy operator, these are not eigenfunction solutions to the momentum operator. And then we take advantage of the fact that our wave functions or eigenfunctions form a complete set. So what we could do if we wanted to know the momentum is we could rewrite our wave function here in terms of the eigenfunctions for the momentum operator. And then we would have a different set of eigenfunction solutions. We'd have a different likelihood of measuring these individual values, and we would get a different value here. And now that's going to be important, the fact that the eigenfunctions for momentum are not the same as the eigenfunctions for the total energy. Now, we'll end off here for today, and we'll continue on next time looking at actually what we're going to be doing with this. So our postulate 4 is going to be the one we'll use the most, maybe with the exception of postulate 1. And it's going to tell us, okay, if I'm measuring a value, if I'm trying to observe something, if I'm doing an experiment on a quantum mechanical system, what am I actually going to measure? What are my chances of measuring one of these values? And we'll look at that next time.